Shall I? Okay, hi everyone. Well, yeah, I'm Dina. It's such a nice welcome, so thank you. I'm really glad to be here. We don't have a lot of time, so let's start. Today we're going to talk about memory traffic performance. I'm going to tell you about how you can reduce your memory traffic and thus make your garbage collection performance better. So specifically, we're going to start with a little motivation because, without motivation, what is there else to life? Then we're going to talk about how to identify that we have a memory traffic problem, which is, of course, an important step in every optimization process. I'm going to show you some specific coding patterns in your code that you probably use every day. We are going to go back a little bit to basics. And you will see how they impact performance, memory traffic performance in your application. And then in the time that we'll have left, I'll also give you another list of tips and tricks of ways you can make your performance even better. So, as I said, we'll start with performance, with motivation. I'm sorry. As you all know, memory allocation is cheap, right? All we have to do is to move the stack pointer from one location to another. It's one command that we have to do. However, it adds up. Start thinking what happens when you keep allocating more and more and more and more. So this very tiny command, of course, it adds up in, computation time. But I think that the major problem here is that it has side effects, or rather one side effect, and that's garbage collection, excessive garbage collection. Generally speaking, when you do garbage collection, you have to stop your program completely from running in order to allow the garbage collector to clean the memory, to go over the entire memory space, mark all the stuff that's being used or not used, move some things around. So that actually pauses your program from running. And so the more you allocate, the more GCs you have to do, and the more time each garbage collection takes. So again, it adds up. So the reason I'm saying that, and I realize it might sound trivial to some of you, but from my experience at least, usually developers when they think about optimization and performance, they think about CPU. How are we going to make this algorithm faster? How we're going to do this in linear time, not quadratic or whatever. And it's not until we suddenly have this weird memory issue coming at us from production and, all hell breaks loose, that we suddenly realize that programming in a managed environment and having a garbage collector is not a magic pill. Yes, it's good. It does stuff for us, but it doesn't mean we don't need to think from our side how to do things better and how to plan for this managed environment. Now, throughout the entire talk, I'm going to show you samples of questions I found online about garbage collection, how it works, how to optimize it, what problems might occur, because this talk, it's not just theory. These things really happen in real life for real people, and it's important to realize that. So here's a good motivational question. There's a guy here, actually, I think this is a Python app, but that's besides the point. He's writing something with Unity, and he had some performance problems. So he ran a profiler, and what he found out that 33% of the time spent in his update method, and remember that the update should be really fast because we're talking graphics and gaming here. So 33% of the time spent in his update method was inside GC collect. Now, I don't know if it sounds a lot to you, but it's a lot. It's a lot of time. You can't let yourself spend so much time in this critical update method doing GC. So I hope we have enough motivation now, and let's try to see how we even figure out that we have a memory problem, because this guy, he had a performance issue. Things were running slow. he had to run a profiler to figure out that, it was garbage collection. So before we dive into code and demos and stuff like that, I want to spend some time to talk about tools and how you identify the problem, because, of course, as I already said, you absolutely can't start optimizing before you diagnose your bottleneck, before you know what it is that you need to optimize. So I think that the easiest way on Windows to monitor your garbage collection and memory traffic performance is using performance counters. Performance counters are kind of like these objects that live throughout the Windows system, and they emit numerical data about different components in your Windows. So they can emit data about CPU usage, about memory usage, about disk usage, about, well, basically really anything that's going on inside your Windows. They're built inside Windows. If you don't know them already, they're there. Trust me. And you don't have to do anything to your applications in order to get this information. You don't have to, God forbid, recompile your application, but you don't even have to restart it. All you need to do is tap into this amazing source of data using the relevant APIs, which I'll mention in a moment, and just, see the data come along and watch whatever is going on there. So specifically for performance counters, there are two tools that come built inside Windows. You don't even have to download them or anything. That's TypePerf, which is a command line tool, and perfmon, which is a nice graphical tool. They both allow you to select which performance counters you want to monitor, which process you want to monitor, and they just either output text output with the data, or you can watch nice graphs, which we'll see in a moment. I will mention as a side note that you can even output your own performance counters from your application. You can for example, I don't know, if you have queue sizes in your application that you want to monitor, or I don't know, response statistics or something like that, you can also output that as a performance counter, which will make your DevOps team probably life easier. But that's not in the scope of our talk. Just know that it's possible, and it might be something worth checking out for you. So, because we don't have a lot of time today, I'm not going to do a live demo of perfmon. Generally, we're going to see lots of screenshots today because I tried to squeeze as much as possible into a 45-minute talk. So this is a screenshot of perfmon. That's the tool I mentioned before, the graphical UI for monitoring performance counters. And the font is small. It's okay if you don't see it. I'll tell you what you see in a moment. What you see here is a graph that I got from a certain .NET C# application that I was running on my machine. And specifically here, I was interested in 4 things. That's the size, the total size of the managed memory. That's the light green line here. The time spent in GC. Percentage of time spent in GC, that's the bold red line. The number of Gen 0 collections, that's the blue line here. And the rate of allocation, which is this sparse, the purplish line over here. Now, the point of this graph is the following. This is the memory, the total size of the memory. And the graph is scaled. It doesn't matter what the exact numbers are. The point is that it seems relatively constant. It doesn't look that the memory is growing or anything like that. We probably don't have a leak in our application. And the rate of allocations is also pretty constant. Everything is running. However, as you can see from the red line here, the percentage of time spent doing GC is 50, 60, at times even, I would say, 85. This is absolutely crazy. It's not normal. It's not okay under no circumstances for our application to constantly spend so much time doing garbage collection. So it's very obvious that we have a problem. There's no leak, but there is definitely a garbage collection problem here. Now, the problem with performance counters is that even though it's very easy to understand that we have a problem, it's obvious that we have a problem, we don't know the origin. We don't know where it's coming from. So we know that our application is busy doing garbage collection, but why? Luckily for us, there's a solution for that as well. And Windows comes along, besides performance counters, it comes along with another framework, logging monitoring framework called ETW, Event Tracing for Windows. It's, as it says, high-speed logging framework, structured logging framework, which supports hundreds of thousands of log messages per second, which is a lot of data. And unlike performance counters, it's not just numerical data, it's a structured log message, which means that you can get a lot more information out of it. And that includes call stacks of where things are happening, data about types, about allocations, about types of garbage collection being done. And like performance counters, it is spread out through the entire system. You have it in user mode and kernel mode, so you have data from operating system structures. Of course, you have data about CPU and memory, both native and managed. You have data about disks. You have stuff from third-party components. In fact, a while ago, I discovered that even Chrome can emit ETW events if you ask nicely. So there's really a ton of data available there. And again, like performance counters, you don't have to, again, God forbid, recompile your application, or you don't have to restart it. Just like before, you need to use the right tool to tap into the data. In this specific case, the tools are not part of Windows, but they are freely available online from the Microsoft website. So just, a little click away from getting all of that rich data. I will mention, some of you might be worried about that. Because we're going to emit so much data, you might be worried about performance. And it is a good thing to think about. Generally speaking, the performance of ETW is very low. But of course, it depends on the amount of data that you emit. So if you have really large data structures that you read, or events that happen very, very, very frequently, yes, you definitely might have a problem. But if it's something rarer and the data is sparse, then it's generally very fast. And again, I want to mention as a side note that you can also emit ETW log messages yourself from your applications and, let your monitors know all sorts of data about what's going on inside. But that's also not the topic of our talk. So just remember that you can do that, and let's move on. So again, we're not going to run live ETW collection, but I do want to show you a pre-recorded file that I got from the same application that we saw before in the perfmon graph. So this time we're going to look at the ETW recording, and we're going to finally figure out where all this garbage collection problem is coming from. So I have the file open here. This is Perfew. It's not very visually appealing. This is true. But it is a very functional UI for everything you might want, almost everything you might want to do with ETW. You can download it for free. It's on GitHub now. It's actually open source, which is pretty cool. So you can see how things are done. So it's there available for you. I'll just show you quickly that there's a collection menu here. It requires admin rights, so it restarted the application. But here you can control all of the data that you want to record. Again, we won't do it now because it takes a while to run the application and record the data and then open the file and so on. But I just wanted to show you that it's all available here. And what we're going to look at now is it here? No, it's not here. Shame. See data. Yes. What I want to show you is a recording that I already prepared before the talk, as I said, of that same process where we exhibited the GC performance problem. So I will open the CPU stacks window here, and I will select my process. It's called Jack compiler. It's actually an exercise from university for quite a few years ago. Not say how many exactly. So what we see here, I know the font is a little small, but I'll read the important stuff for you. What we have here basically is just a list of all the functions, well, not all, but like functions that were called during the application recording time. And we see the amount of time that these applications run. And we can get the statistics both inclusively and exclusively. Specifically, if I sort them inclusively, then obviously 100% of the time is spent in my main method. And if I scroll a little down, and I already know the result, so I'll just scroll to wherever it is that I want to show you, we can see that 45% of the time is inside CLR alloc. So we spend 45% of the time allocating objects, which is pretty interesting in itself. Okay, so that's a good thing to think about. By the way, we can already see here, I skipped it because I want to show it a little differently, but in case you noticed, you can also see here that we have lots of write lines, and we have string concat, which is suspicious. All right. String concat specifically takes 56% of the time, which is really pretty crazy if you think about it. So this is CPU data. Luckily for us, from this ETW recording, I can also get memory allocation data. I have call stacks and type statistics about what was allocated in my application. So I will go to the memory window here, and I will open this alloc view, and again select my Jack compiler. And straight away, I can see a list of all the types that were allocated during my recording, and the size of the recordings. And specifically, this is sorted by the size. We can see that the largest thing, and that's like, gosh, I don't know, there are a lot of zeros here. I'm not sure like if it's gigs, megs, whatever, but it's a lot, okay? It's a lot of bytes. We're allocated as large objects. So we probably have arrays or something, probably something large. And then, you know what? It's basically large object. So we also see that we have strings and char arrays and some token of some sort, but like 99% of the allocations are these large objects, which currently I don't know anything about. So I will double click this large object, and I will see the call stacks of where these large objects were allocated. And what I see straight away here is that I have this object in my code, the Jack compiler, which writes stuff to the screen. And let me see if I can make it a little better by loading symbols. No, it doesn't help. Oh, yes. Good. And what we can see here is that we have an assignment method which allocates a lot of data, and we have another call method in our code that allocates a lot of data, and another method, and so on and so forth. I can now go to the code and see what's going on there. And by the way, I'm sorry, I forgot to mention it. We saw it before. All of this, in turn, calls the string concat. And we know the string concatenations might be a problem because they cause a lot of intermediate strings which are, concatenated to each other again and again and again. And so if I open the code, we'll go to the C code generator. Here it is. Oh, sorry. Here it is. Specifically, we saw, let me see, I forgot the name of the function. I apologize. What happened? Here it is. Yes, we have the compilation output text writer. Where is it? You know what? I'm sorry, I can't find it right now. I found it later for you and I'll show you. But the point being is that we have a class here which compiles code. And being a compiler, it deals a lot with strings and writing stuff to the output being the result of the compilation. And so it deals a lot with string concatenations. And I'm sorry, I can't find it now. I will find it later. The point is that it uses the plus operator for adding strings instead of using string builder, which concatenates string in a much more efficient way. And so this is the reason that we have this problem in our code. Good. So the next thing I want to talk to you about is static code analysis. This whole thing could have been avoided if, when I wrote that plus operator in my code, I'm sorry, I have a sign of 20 minutes and it's making me nervous. It all could have been avoided if, when I wrote that plus operator, I knew that it was going to cause allocations. And that's something that static analysis can give me. Static analysis is based on the idea that I give my code to a tool which goes over it automatically and detects certain coding patterns which are known to be inefficient in memory usage. For example, string concatenation, which is obviously very easy to diagnose. Another thing it could find for you is forgetting to dispose of an idisposable. And of course, it's not limited just to memory problems. It could also tell you that you didn't pass enough parameters to your console write line, or that you, used an uninitialized variable or stuff like that. There are a lot of tools available out there, starting from Visual Studio, the built-in static analysis, ranging through ReSharper, and tools like Coverity, which cost thousands of dollars per year. So there are a lot of options there. Here's an example. Oh, good. This is from the Jack compiler. It's good that I didn't find it in the code. You have a screenshot here. This is an example of an add-on called CLR Allocation Analyzer. I think that's what it's called. And it actually shows you inline in your Visual Studio where your code causes allocations. So we can see here that we have all these squiggly lines. That's because this concatenation causes memory allocation. And we have this memory allocation here, which we're going to see later what happens there. So you can get rid of these places while writing your code, which is pretty cool. Now, Static analysis is very convenient, but still there are cases where it's very hard to diagnose problems without actually running your code and getting some sort of temporal analysis of what's going on. So you can use a dynamic memory profiler to track allocations, track memory usage, track whatever is going on inside your code. And again, there are lots of commercial tools out there. They do cost money. A lot of the times they cost a lot of money. What you pay there, though, is the convenience, because a lot of these tools actually use ETW as their source of information. So theoretically, you could do the same thing yourself. However, they would usually provide nice graphical UIs for you, nice screens to see, to diagnose the problems easier, and to even pinpoint the problematic areas for you. So for example, I have a screenshot here of a tool called .NET Memory Profiler, which I ran on a certain C# application. And what we can see is that I took several snapshots of the process's memory, and the tool helped me compare them. And what it found out is that the number of response objects grew quite significantly between one snapshot to another. So it's possible that I have a memory leak. Of course, it's not evident, but it's possible. So if I want to know what's holding all these objects in memory, I can just go to a different screen, and it's going to show you what's keeping them inside. And specifically in this case, there's a static response cache object that's holding all my stuff. Now, it might be a bug, it might not be a bug, but the point is that the tool helped me understand what's going on, why memory is high, why I have all these objects in memory. Okay, good. So now we definitely know how to diagnose that we have a memory problem. Let's try to understand how we even got to this situation, how we managed to get ourselves in a situation where we have so many memory allocations. Like before, we'll start with an example. This is a question from someone who was keeping a dictionary, something with vectors. And what he found out was that each time he read from the dictionary, and again, I stress out, only read from the dictionary, there was memory allocated. So again, he wasn't inserting anything inside, he was just, getting data. And yet, memory was allocated. He was surprised, because dictionaries are supposed to be pretty efficient, right? So we don't have a lot of time, so I won't ask you if you know what the problem is. The answer is that there is boxing, because his vector is a struct, and a dictionary is a generic data structure, and there is boxing involved when he got this data outside. So let's try to understand, though, how severe the effect of boxing might be. So specifically, what I would like to measure is the effect of boxing when we have an array of data structures that we need to traverse in order to search, or something like that. So what we're going to see is an example where we have a data structure, and everything that we have inside is a single int, and we want to measure how long it takes to search an element inside this array. Since we're going to search, we're going to have to compare elements, and there are 3 ways to compare elements. The first one is just, to use the default implementation. The second one is to override the equals method. We're going to look at some code in a moment. And the third way is to implement IEquatable. And what I would like to do is to measure the difference in timing between all these options. So let's look at the code. I'm going to use a benchmarking library called benchmark.net. It's generally hard to do benchmarking correctly, so this library, which is freely available on NuGet, is going to make life much easier for me. And what we'll see here is the 3 versions of our struct. So we have just, a struct with an int, and then we have a struct with an int, which implements the equals method. Makes it possibly a little easier to compare because I know that all I need to compare is just the value inside. And then I also have the I-equatable version, which is actually the easiest to implement because I don't even need to check the type of the input. I just know that I get this struct and I compare the contents. And what my benchmark is going to do is that it's going to search. It's going to have a list of such data structures initialized with all sorts of data. And I'm going to have 3 benchmarks, and each of them is just going to search the list, the relevant list for the last element. Since it's the last element, it's going to end up traversing the entire list. Benchmarking takes a lot of time because it repeats the test over and over again to collect statistics. So we're not going to run it now. So I will just show you the results that I prepared beforehand. So these are the results. The first thing that I want to do is to concentrate on the second 2 rows. That's comparing the case of just implementing, overriding the equals method, and the case of actually implementing the I-equatable interface. Note the difference in allocations. And of course, the difference in runtime. That's a factor of 3, which is quite a lot. So let's try to understand what's going on. Searching is easy, right? We just need to go over all the elements and compare them. However, comparing primitive elements is straightforward, but if we have our own specialized structure, it's not clear how to compare it. So we need to create the correct comparer in order to be able to, to search for our element. And it turns out that this is where the difference lies, because generally there is an object equality comparer which holds for all data structures. However, if your data structure implements I-equatable, then it has a different kind of comparer. And it makes sense, really, because if you implemented I-equatable, then obviously, you want to use it, use your own function in order to compare objects. So this is the general comparer. Basically, what it does is, just call x equals y. But let's try to understand where allocations are coming from. So this is the generic general equals method. It gets an object as an input. But in our case, y is a struct. So it has to be boxed when passed to equals as an object. What about x, though? X also has to be boxed, because this equals method is a virtual method. And so in order to call this virtual method on a struct, we need to box it in order to use the method table and everything that needs to be done to call virtual methods. So we have 2 boxes here. Okay. What about the second, the I-equatable case? The C# code looks the same, right? Because everything we need to do is, just call x equals y. But in this case, the equals method is bound to the I-equatable interface equals method. And that method receives not an object, but the actual struct as an input. So y doesn't have to be boxed. What about x, though? Well, it's not evident from the code here, but it's actually a JIT optimization. It turns out that when you call an interface method on a struct, on a value type, the JIT just translated into a direct function call. And so there's no boxing there either. And that explains the results. We don't have any allocations in the second version. And indeed, if we look at the ETW recording of the first case, of just the equals case, we can see that 45% of the time is spent, 41% of the time of the equals method is spent inside allocating objects. Just one word about the general case where I didn't implement any equals method. yes, we can see that there are more allocations here, but it doesn't explain the, what is it, like a magnitude of 50 times worse. Here, the problem is just all the reflections, because the semantics of value types are member-wise comparisons. If we don't implement the equals ourselves, the compiler is going to have to go over all of the members and do a lot of reflections, and that's just, it's not efficient. So in any case, you should always remember to implement equals for your structs. Next, now we're experts in boxing. Let's see what happens when you use lambdas, which is something you obviously don't hesitate before using. So lambdas are just a syntactic sugar. When we write the code here on the left, it's actually translated to the code on the right. The compiler creates kind of a helper class, which has a field for each of the captured variables, and it creates a method which implements the actual lambda code. So all of this is translated into an instantiation of the helper class and an invocation of the method. So let's see the effect of capturing on our performance. Here it is. So we're going to see 4 options of capturing state. What we're going to see is kind of a simulation of a scenario where we have tasks. Tasks use lambdas, right? And these tasks want to use some data from the outside in order to do some manipulations. Okay? There is nothing smart about the specific action that I'm going to do. It's just going to add up some functions, and it has synchronization issues, so ignore that. That's not the point of the demo. We're just interested in the capturing part. So the first option is to just, capture the data using the lambda, which is probably would be, the most straightforward code that we can write. We have so-and-so elements. For each of them, we create a task. This task adds some data to a variable. Another option would be to use a special task API, which actually doesn't require capturing, but rather passes the input as a parameter to the task start method. So that would be our second option. And another 2 things I wanted to check is what happens if we don't have any data to capture at all. So here we just use some global default data, so there's no capturing. And here we actually do the exact same thing, only I gave this method a name. I called it add function, and I passed it to the start new API. So let's look at the results. These are the results. The first thing that I want you to notice is that there's a general correspondence between the size of allocations and the time that the benchmark took. And I think that it shouldn't surprise you by now. Let's try to understand, though, why this happens. So let's look at the first case. In the first case, we have to allocate data. Obviously, there's no way around it. And since we need to capture this data, we also need to allocate our helper class. And then finally, we need to allocate the action that we're going to run. And this happens for each iteration of the loop. In the second case, well, again, of course, we have to allocate the data. However, it would seem that in this case, since there is no capturing done, the compiler is smart enough not to create the helper class for each iteration, but rather instantiate it once and save it in a static field of the compilation result. And even the action itself is instantiated once and cached inside. So basically, the only thing we allocate over and over again is just the data. Third case, obviously very easy. There's no data capturing. There's no data creation. The only thing that we have is, again, this method here that's only instantiated once, and the action, which is also cached. And lastly, and this is the interesting part here, I don't know if it's a feature, it's probably a bug, but it turns out that when you use method groups, the compiler doesn't do that optimization, caching the result of the instantiated action, and it just keeps instantiating the action over and over again, which is really weird. So next time ReSharper tells you, use a method group here, make your code nicer. Yes, the code is nicer, but there's a penalty, and it's weird, but that's just the way it is. And this really explains the results. You can now understand fully why these allocations happen and why certain cases have more allocations than the other. Specifically, if I compare the method group with this passing a state case, probably just the data structure takes less memory than the action class because the total size of allocations is smaller. Just an interesting piece of trivia. Good. Now, if we add all of this together, collections and boxing and lambdas into using LINQ, we can understand that LINQ is really the culmination of all evil. Why, you ask? Let me show you something. I will go over it really, really quickly because it doesn't really matter, the code itself. The point is that I have some mathematical calculation that I want to do. And it's basically going over a whole bunch of numbers and calculates averages, sums, whatever. And I can do it in 3 different ways. I can just do it with loops and hardcore, straightforward code. I can help myself a little by introducing some helper C# classes. Or I can go all the way to LINQ and do this thing. Now, in this specific case, I don't even think that the code is simpler because it took me a while to get it right. And again, it really doesn't matter what it does. Just trust me that all 3 functions do the same thing. They output the same number at the end. I checked, okay? And I ran these in benchmark.net. And these are the results. They really are astounding. There is a factor of 10 between the straightforward loops and the LINQ version. So just remember, I really, no words, okay? These are the results. Do whatever you want with it. So in like the 3 minutes that we have left, or maybe 5 because you stole a little from me, I do want to give you some general tips about what else you can do to make your applications even better. So the first thing is don't call GC collect, okay? It's okay if you do it for debugging or in order to understand what's going on, but you need to trust the CLR that it's going to call GC collect whenever it sees fit, whenever it actually doesn't have enough memory to run. Because remember, you have a performance problem, yeah, and you want to use GC collect to solve it. But you already have a problem, so you're going to call GC collect, which is going to take time, and it's going to pause your application for even more time. How can that help? Okay? Not a good idea generally. So again, based on a real-life story, there's someone here using a third-party library. He has performance issues, and he thinks that this third-party library calls GC collect and causes, pauses and stops to his application. So, real-life story. So real-life story that we even have this in our own code. This is it happened like a week ago, okay? This was like sheer luck that this happened. My manager sent me this email asking whether I think we should still be calling GC collect every minute. Now, it doesn't really matter why we did it in the first place. There was a reason. But the point is that just 3 weeks ago, we had to debug a performance issue with one of our clients, and we ran ETW, and it turned out that our GC collect thread was consuming 10% CPU. So it's true that 10% is not as severe as some of the examples that we saw before with 50, 60, percent GC, but still, it's 10% that could have been used better. So there's really no reason not to do that. And yes, my reply to the email was, yes, let's remove that thing. Another interesting story, there's a guy here who was using some sort of producer-consumer kind of thing. And his application kept crashing with out of memory. So in a desperate attempt to make things better, he inserted GC collect. He thought there was some bug in the CLR, whatever. And it solved the problem. As we know, GC collect does not solve problems, it just creates more problems. And indeed, after he investigated the thing further, what he found out was that it was just a coincidence. Because what happened was that he put this GC collect in his producer thread. And what it caused is that it introduced a delay which allowed the consumers to consume the data before the producer produced more. And so this magically solved the problem, but it really was just a coincidence. My second suggestion is to use value types when appropriate, of course. Value types use less memory than objects because they don't have headers associated with them. And when you allocate arrays of value types, then the entire memory is going to be continuous rather than sparsed out throughout the memory. So aside from using less memory, it also helps with cache misses. So if you have an application like image processing, where you rely on a lot of array processing and mathematical calculations, you're definitely going to use, for example, for your point data structure, you're definitely going to use a struct. Again, based on a real story, there was a guy here who was implementing a ray tracer in C#. Now, it's besides the point why the hell he would be implementing a ray tracer in C# rather than in C++. Maybe it was an exercise, I don't know, doesn't matter. Point being, he had very severe performance issues, and they were all magically solved when he switched his vector class to being a struct. Because of course in graphics, a lot of arrays of vectors, so this was definitely a bottleneck. Next suggestion is to find your expensive objects and pool, buffer, reuse, whatever word you prefer, because you just don't want to allocate over and over again. And there are APIs online that can help you with that. There's a NuGet package by Microsoft for an object pool. It's hard to implement an object pool correctly on your own, so try to use something reliable. Another thing you might definitely want to check out is system buffers, which allows you to efficiently use subarrays, which in turn would allow you to kind of manage memory your own. If you have a lot of arrays that you deal with, especially in networking and like byte arrays and stuff like that, then you might want to consider managing memory on your own. Allocate a large array and then dispatch parts of it to different places in your application. So system buffers will help you with that. Again, based on a real story, a WPF application which had to display changing images over time. You could just create a new bitmap source each time, or you can use the more correct API, writable bitmap, which allows you to allocate an image just once. And we know that images tend to be large. So it will allow you to allocate an image just once and then update the pixels without having to reallocate the data buffer over and over again. And finally, try to avoid finalization. It can do all sorts of weird stuff to your application, like resurrect objects. You already saw the case of a producer-consumer that we saw before, that he had some sort of memory leak. And with the finalization queue, it's actually a producer-consumer thing where the consumer is the finalizer. So if your finalizer is not quick enough, you are going to end up out of memory. So try to use iDisposable as much as you can.
I'm afraid we are out of time, so we have to move straight to the questions.
Yes.
Let's thank Dina for the great talk, and let's move to the questions.
Yes.
So let's start here.
Thanks for your great talk.
Thank you.
I have a question about .NET Core. Are there any tools that help me with .NET Core, especially if I run production on Linux?
Well, I have to admit that I don't have any experience with .NET Core. From the little, experience that I do have that I tried, it was hard. Tooling was hard. If you're in Windows, though, ETW should work, regardless. There's no ETW on Linux, so I can't, tell you about that. There are other tools on Linux available, but performance counters, it all should work. So all these diagnostics tools, all the profilers, it's supposed to be the same. I can't speak from my own experience, but there's really no reason for it to work differently.
Thank you very much.
Thank you for the presentation. I have a question about a very interesting setting in .NET Runtime, which is called GC Server.
Yes.
Have you tried to experiment with this setting?
Yes. Generally in performance, it's all about experimenting, because even if I write, online that I was doing this and that, and the GC server setting worked better for me, or something else worked better for me, it doesn't mean that it's going to work better for you. So performance is really about experimenting and benchmarking your own specific code. And it's definitely something that you should check out. Generally, I haven't, I didn't speak a lot about GC, and I did lie a little when I said that it pauses your application completely, because there are advances in the GC world, and it doesn't, pause your application completely.
Thank you. I can tell a little about my experience with this, because...
I suggest that we move this to the coffee break or to the after party, because we have some other questions and the time is pressing. So I guess we have time for 2 quick questions.
Thank you for your presentation. And I'd like to ask you one question about limitations of usages value types. For example, when we switch to value types, we know that they stored on the stack. And what if you have value type which contains 10 fields?
I'm sorry, I can't hear you very well.
What if you have value types which contain a lot of fields of integer values? For example, 10 values, and you must process these value types on the stack and copy into the array, and will Stack Overflow exception exist or something like this? So what is the limitations of usage value types comparing to objects?
Yeah, so I forgot to mention it. Value types, their whole point is that they're based on values, which means that they're passed to functions as copies, and they're returned from functions as copies. And it definitely has a cost. If you have a very deep recursion with a lot of value types on the stack, so I guess you might get a Stack Overflow or something like that. And it shouldn't be your default. Definitely. The default should still probably be classes. Of course, like I said before, in performance, everything is about, checking your specific case. As a rule of thumb, the default probably should be objects. However, in the specific case of large arrays of things like points, of objects that you need to go over a lot to process, you should definitely consider arrays of structs, because just the locality alone, the cache misses, are going to add a huge benefit to your application. And again, there's just no way around it. You have to test your specific case and see what works better for you. Unfortunately, I can't have a general answer.
All right, so unfortunately we are out of time, so that was the last question, and now Dina, you as a speaker get to pick the best question, which gets a small prize from the organizers.
Oh wow, gosh, remind me the question. I think the last one.
All right, that's cool. So let's thank Dina again, and we have a break for the lunch.